All right, welcome back to the deep dive. We take your source material, break it down, and help you build mastery. And today, we're diving into something really foundational for software folks, UML class diagrams. Think of it as the architectural blueprint for code. So our goal here, our mission, is to give you a really solid grasp on how to read these things, understand them, and actually use them. They're just critical for object-oriented programming. We've got a great set of sources here that cover everything from, the tiny symbols up to the whole system view.
Yeah, and it's super important stuff because the UML class diagram, it's kind of unique in the UML world. It's what we call a static diagram. It shows the structure, the vocabulary of an application, how things are, not necessarily how they change over time. And the key thing, it's pretty much the only UML diagram type that maps like almost directly one-to-one with OLO languages. Think Java, C++, Mino. If you could read the diagram, you basically understand the code structure that has to be there.
Okay, let's unpack that a bit then. If it maps so directly to code, the notation must be, well, pretty specific, right? What exactly does a class diagram tell us inside those boxes, besides just the class name?
Oh, absolutely specific. Yeah, it has the class name, of course, but it also spells out the access levels, public, private, and the data types for all the variables, the attributes. And for the methods, the functions, it gives you the full signature, access, name, what goes in, what comes out, the return type. It's essentially the complete contract for that piece of software.
Right. So let's get into the visual side. When you first look at one, you see these boxes, usually split into 3 sections. For someone aiming for mastery, like our listeners, it seems we need to look past just the box shape and really focus on what's inside those sections.
Exactly. That information density is key. And those 3 regions are standardized, which helps. So the top region, that's just the name of the class, square, user account, whatever, exactly as it would look in the code. And interestingly, that name, that's the only thing that's technically mandatory in the whole UML box.
Really? Only the name?
Yeah. I mean, in theory, you could leave the other 2 empty, especially early in design if you're just sketching things out. Then, the middle region. This holds the attributes, your member variables, fields, whatever you call them. And the notation here is crucial. You've got the access symbol, the variable name, a colon, then the data type. So for like a square class, maybe you'd see side.double. Instantly tells you it's a private variable named side and it has to be a double.
Okay, side double. And you mentioned UML is precise. So can you add more detail there, like maybe a starting value?
You absolutely can. If the design needs an initial value, you can add it right after the type, maybe like evo. Yep. So side.double evo 0. And then finally the bottom region. That's for the methods or operations. This part usually has the most detailed access, method name, the parameters it takes, and importantly, the return type.
Okay, let's zoom in on that access part. You mentioned the symbols. That seems like where the diagram really starts dictating the code's behavior, especially around encapsulation.
That's exactly right. That first little symbol you see next to an attribute or a method, that's its visibility. It tells the developer exactly who or what can access that element. It's the direct link between the diagram and those access modifiers in the code.
Right, like public, private. So we need to really know these symbols. What are they?
There are 4 main ones you'll see. The minus sign, that's private. Only visible inside that specific class. Stronger protection. The plus sign, plus kfill, that's public. Visible to basically everyone, all other classes. The hashtag. This one means protected. So visible to the class itself and also to any classes that inherit from it, its subclasses. And the last one, tilde. This usually means package or default visibility. Visible to classes in the same package. You don't see it quite as often, depends a bit on the language.
Okay, minus for private, plus for public, hashtag protected, tilde, package. Got it. Here's where it gets really interesting, showing that density. Let's try an example with a method. Say we're designing some internal calculation logic, maybe a method called calculate foo. We want it protected and needs to take in an integer, let's call it x, and maybe a character c, and it should return a string. How does that look?
Perfect example.
Right.
So protected means you start with a hashtag, then the name calculate foo, then parentheses for the parameters, x indoc c char. Notice the name, colon, type format again, and finally a colon and the return type, string. So the whole line is just hashtag calculate foo, x int t char dot string.
Wow. Okay, one line, and it captures the access, the name, the inputs, the output. That's really efficient.
That's the power of it. It's very dense, very precise language once you know the grammar.
All right, so sticking with methods for a moment, what about common patterns like constructors or getters and setters? How do they show up?
Good question. Constructors are special. They're almost always public, so they start with a plus s. Conventionally, they have the exact same name as the class itself. And the crucial bit, they don't have a return type listed, not even void. So for our square class, if it takes the side length when created, it might look like plus square dot double.
No return type. Okay, that's
Yeah.
a key detail. And then for managing those attributes, like our private side variable, we usually have getters and setters.
Exactly. Accessors and mutators, standard practice for encapsulation.
Oh,
Setters or mutators are often public, plus S. If their only job is to set the value and they don't need to return anything specific, like a success flag, you mark the return type as void. So setting the side might be plus set side dot double. With the void, getters or accessors are also usually public.
yes.
Their job is to return the value of the field. So they return the same type as the field they're accessing. For our side, which is a double, it would be plus get side dot double.
Simple enough. Public, return the type, or void for setters. Now, you mentioned something advanced. Parameter directionality. Why would we need to specify if a parameter is in or out? Isn't it usually just in?
Yeah, in is the default and often implied. But specifying directionality explicitly using in, out, or in, out becomes really important in certain contexts. Think about designing APIs or working with languages where passing by references in the default, or maybe performance is critical. Specifying out or in out is a clear signal about the intent of that parameter. Out specifically tells you, this method is going to put a value into this parameter to send it back to whoever called the method. The information flows out through that parameter. It clarifies the contract, makes the behavior unambiguous, especially across different system boundaries or languages.
Ah, okay. So it's about removing ambiguity in the data flow. Makes sense for complex interactions. We've gone deep into the symbols, the syntax, the minus signs, colons, return types. But let's pull back up. Why invest all this effort? How does mastering this notation really help when we're talking about, the whole system architecture?
Yeah, it's easy to get lost in the details, but they serve a bigger purpose.
Hmm.
It connects that precise notation back to the fundamental goals of design. These diagrams aren't just documentation you write afterwards. They're a core part of the design process itself. They directly support forward engineering, where you can actually generate skeleton code from the diagram, and also reverse engineering, creating diagrams from existing code to understand or refactor it. Fundamentally, they provide that clear, unambiguous shared blueprint of the system structure. Everyone on the team sees the same plan.
And crucially, the level of detail isn't always the same, right? It depends on what you're trying to achieve at that moment. That's where those different perspectives come in.
Exactly. Understanding the three perspectives is maybe one of the biggest takeaways for using UML effectively in practice. It's all about matching the diagram's detail to the current stage of development. So first, you have the conceptual perspective. This is the highest level, like a 30,000-foot view. You're modeling the key concepts in the problem domain, using the language your users or stakeholders understand. Here, you might honestly just have the class name, maybe some key relationships. Details are minimal.
Okay, high-level business concepts. What's next?
Next is the specification perspective. This focuses more on the interfaces between software components. Think abstract data types or ADTs. You're defining what services a class offers, its public face, its contract, but not necessarily how it implements them internally. So you definitely show public methods, public attributes, but probably hide the private stuff.
So focusing on the what, not the how, and the last one.
That's the implementation perspective. This is the most detailed view, the one closest to the actual code. Here, you're describing exactly how a class will be implemented to meet that specification. You'll include everything: private attributes, private helper methods, the exact data types, dependencies. This is the full blueprint for the developer writing the code.
I see. So back to your earlier point, the name being the only mandatory part, that makes sense now. If you're working at the conceptual level, or maybe even specification, listing every single private helper method would just be noise, right? It would distract from the main architectural points.
Precisely. The diagram has to serve the conversation you're having at that time. Are you discussing domain concepts with a client? Conceptual view. Are you defining an API for another team? Specification view. Are you detailing the internal design for your own team? Implementation view. It's about choosing the right level of detail for the job at hand.
Okay, that clarifies a lot. But systems aren't just isolated boxes. The real power comes when you connect them, show how they interact. So let's talk about the lines between the boxes, the class relationships.
Right, this is where the overall structure emerges. How do these components actually work together? The most fundamental one maybe is inheritance, or technically generalization. This shows that classic is a relationship, like a checking account is a type of account. We draw this with a solid line, and the key visual is a hollow arrowhead pointing from the subclass, the child's checking account, up to the superclass, the parent account. Oh, and a quick note. If the parent class account is abstract, meaning you can't create an instance of it directly, its name is often shown in italics on the diagram.
Hollow arrow for inheritance, pointing to the parent. Got it. What's the most basic connection type?
That would probably be association. It's just a general structural link. It means two classes know about each other, they interact somehow. Like a doctor class might have an association with a patient class. It's typically just drawn as a solid line connecting the two boxes. Pretty simple.
Okay, solid line for general association. Then you get into those whole part relationships, which seem important. Aggregation and...
Aggregation and composition. Yes, both represent whole part structures, but there's a crucial difference in dependency. Aggregation is the looser form. The part can exist independently of the whole. Think of a team and its players. If the team disbands, the players still exist, right? They can join other teams. We show aggregation with an open diamond shape on the end of the line connected to the whole class, the team.
Open diamond, part can live on its own, so composition must be the stricter one.
Exactly. Composition is a much stronger ownership. The part cannot exist independently of the whole. Its life cycle is tied to the whole. If you destroy the whole, the part is destroyed too. The classic example is maybe a building and its rooms. You demolish the building, the rooms cease to exist in any meaningful way. Or in software, maybe a shopping cart and its line items. The items only make sense within that cart. This is shown with a filled diamond on the end of the line connected to the whole class.
Filled diamond part dies with the whole, okay. And usually near these lines you see numbers, right? Multiplicity.
Yes, multiplicity or cardinality. You hear both. That adds constraints, business rules essentially. It tells you how many instances of one class can be related to one instance of the other class. You'll see things like 1 for exactly 1, 0.1 for 0, or 1 meaning it's optional, or 0 for 0 or many, 1 for 1 or many. For example, maybe an order must belong to exactly one customer. But a customer can have 0 or many 0 or just orders. That adds critical information.
Right, the numbers define the rules. And is there one more main type of connection, something maybe less structural?
Yeah, the last common one is dependency.
Yep.
This is a weaker relationship than association. It basically just means one class, the client, uses another class, the supplier, in some way. Maybe it receives an instance as a parameter. Maybe it calls a static method on the supplier. The key implication is that if the supplier class changes, the client class might need to change too. It depends on it. We draw this with a dashed line and an open arrow pointing from the client to the supplier it depends on.
Dashed line, open arrow, pointing to the thing being used. Okay, so putting it all together. We've gone from the tiniest symbol, like a minus sign, all the way up to these complex diagrams showing inheritance, composition, multiplicity. What's the big takeaway for someone listening? Why does this matter?
I think the essential value, the real takeaway, is clarity and communication. UML class diagrams, when done well, are arguably the most precise tool we have for communicating software structure. They force you to be rigorous in defining components, their responsibilities, how they connect. This ensures that when the code actually gets written, it follows that intended architecture consistently.
Yeah.
That's absolutely vital for building complex systems that don't fall apart. You know, it helps everyone stay on the same page.
That makes sense. It's a shared language. Now, thinking back to the start, we said a class name is the only truly mandatory thing in that box. From an architectural viewpoint, why is that minimalist approach even allowed? Why isn't more detail always better?
That really gets to the heart of the design challenge itself, doesn't it? It goes back to those perspectives we talked about, conceptual, specification, implementation. When you're first sketching out a system, maybe talking with non-technical people about the core concepts, conceptual view, listing every private variable and helper method is just counterproductive. It's noise. It drowns the important structural ideas in low-level detail. The real skill in using UML is constantly asking yourself, what level of detail does this specific diagram need right now to effectively communicate the intended point for this audience? Is adding more detail actually helping clarify the fundamental organization of the system, or is it just becoming a distraction? That balance, deciding when to add detail and when to deliberately omit it, that's where the real mastery lies. It's a judgment call every single time.
That's a fantastic point. It's not just about knowing the rules, but knowing when and why to apply them or even break them slightly for clarity. Well, hopefully this deep dive has given you, our listeners, a much stronger map for both reading and creating effective UML class diagrams. Here's something to think about before our next deep dive. In your own work, in the technical discussions you have, which perspective, conceptual, specification, or implementation tends to dominate? And how might deliberately shifting that perspective, maybe by adjusting the level of detail in your diagrams or explanations, lead to clearer communication? Food for thought. Thanks for joining us, and we'll see you next time on The Deep Dive.